Okay, this week's video is on chapter 11 in our textbook. We're skipping 10, we skipped 8 and skip 10. There's nothing wrong with those chapters. Just in the time we have, I think this is a better use of our time. So this chapter talks about the limitations of what we can solve using the techniques that we've covered so far. So as it says right there at the beginning, we've covered dozens of algorithms that solve a bunch of problems, but there are still a good number of problems that we can't really solve very well. Either we can't solve them at all algorithmically, or we can't solve them as it says here in non-polynomial time, which means there's got to be some very exponential or ugly algorithms. Okay, so we're going to go through some sections here on ways that we can deal with this. In section 11.1, we're going to talk about these lower bounds, okay, which are in essence an estimate on the minimum amount of work that you need to do to solve a problem. Okay, so it gives you a lower bound on the efficiency that you can expect. So we'll be able in this chapter to say, for example, that for a sorted array, okay, that we're going to get the best possible thing that we can, or sorting the best possible we can with like a quick sort or a merge sort. Okay, and we'll continue that on in section 11.2, talking about decision trees. So we can use that technique to establish the lower bound that they talked about in section 1 on merge sort, for example, to see can you get anything faster? Okay, it turns out that you can't. Okay, so 11.3 is an interesting, more theoretical chapter talking about questions of intractability or problems that cannot be solved in polynomial time. And we'll go through what's known in this area, and we'll be left with the really the biggest question in computer science as far as that goes. The last section's on numerical analysis. It's unlikely we're going to get much out of there. Okay, so I think that I'll see when we get there, but I think for mostly we're going to skip over that, at least in any kind of reasonable way. Okay. So this first section talks about the lower bound arguments. Okay, so we're going to try to figure out in a perfect world how much processing has to be done. Okay, so what's the least it can do in order to find its answer? Okay, so if you know this lower bound, the theoretical lower bound, okay, then there's no reason to look for anything better if you have something at that level, more or less. Okay, so we'd say that's a tight bound. We already know something that more or less does that. Okay, but if there's a gap, okay, which means theoretically there's a much better, much more efficient algorithm, we just don't know it yet, well, then either there's another algorithm out there, okay, or maybe your calculation of the lower bound wasn't correct. Okay, one or the other. Okay, so we're going to look at some ways that we can establish these lower bounds. Okay, so we start with the idea of a trivial lower bound. Okay, so a trivial lower bound means you're just looking at how much or how many items of the program's input have to be processed, and then how many numbers of output items need to be produced. Okay, so an algorithm, if it has to read all the input items it needs and then to process and write all the output, that gives you a trivial lower bound. Okay, so for example, we're looking at an algorithm for generating permutations of n distinct items. We've looked at that before. It's got to be in the big omega of n factorial, because that's the size of the input, right? We've got the input of n, and then we've got the output of n as well. Okay, so that's a very complicated process that we talked about before. Okay, so another example they're given here, the problem of evaluating a polynomial of degree n. Okay, you have to see that all the coefficients have to be processed for that to be the case. So the algorithm then must be a big omega of n. Okay, and this lower bound is tight, as it points out, because the left to right evaluation algorithm and Horner's rule are both linear. I think we didn't talk about Horner's rule, but if we did, that's going to be correct. Okay, and again, we can say a trivial bound for computing the product of two n by n matrices is n squared. So we have to do that. We have to process 2 times n squared elements in the matrix and generate 2 n squared elements of the product. Okay, There's nothing yet that we have done that's close to that. So that is a bound that is not tight. So we don't know yet. Okay. So the trivial bounds are often ridiculously low. Okay. So for example, the traveling salesman problem that we've talked about, where you're trying to find the most efficient route for a salesman to travel from one city to a bunch of other cities without going back and ending up where he started from. That problem, if we look at the lower bound, comes to n squared, okay? Because you have n times n minus 1 divided by 2 intercity distances, and the output is a list of n plus 1 cities, okay? But this bound is insane because there is no known algorithm that gets you anywhere close to that, okay? It's one of the real unsolved problems of computer science, okay? So that's one issue we have here, that it really, it's a lower bound, but it could be way, way lower and not reflect the complexity of the program, okay? There's also this information theoretic argument, okay? So in this case, we're looking about the number or the amount of information it has to produce, okay? So if you're looking at, as it says here, the well-known game of deducing a positive integer between 1 and n, someone is going to answer yes, no questions. The uncertainty that any algorithm solving the problem has to resolve can be measured by the log 2 of n. Okay, so that's the number of bits needed to specify a particular number among the n possibilities. Okay, so the way to look at that is that when you look at the number of bits in the question, say that whatever n is, it could be represented in 4 binary digits. 1111 be from 000 to 1111. Then the yes no questions you can ask on each of those bits and you can get to your answer in that way. Okay, so that becomes the information theoretic argument for that. Okay, and we're going to talk about this idea more when we look through the decision trees. Okay, so and also we talk about it in section 11 too. Okay. So another way we can do this is that we can look at the worst possibility that we could have. Okay, so we're doing an example here of the adversary method. Okay, so we're looking at, we have a malevolent but honest adversary. Okay, so it's going to follow the rules, but it wants to make things take as long as possible. Okay, so what's going to happen when you consistently take the worst choice that you can take? Okay, so this goes to an example we talked about when we're doing the merge sort problem. Okay, that you're going to have 2 sorted lists of size n. You're going to merge it into a new sorted list of size 2n. Okay, and we did this by merging, by comparing the first elements of each one. Okay, so can we do that any quicker than that? Okay, it turns out that we can't. Okay, so again, using the adversary method, you're going to reply true to this comparison only if the elements that you're basing on, element positions, are also less than. Okay, and this will force any correct merging algorithm to produce only the combined list consistent with the rule that it shows there. Okay, so by choosing this as the worst case, okay, then you're finding out that is the lower bound on that problem. Okay. Okay, then you've got here the problem reduction. Okay, we talked about this before. So if we have an algorithm for problem P, if we can get that by reducing it to problem Q, which we can solve, okay, we can do a lower bound in a similar way. So if we can show that a problem P is at least as hard as another problem Q, we have to reduce Q to P, okay? And if you can do that, then you can show that, okay? So here are some of the things that are often used for that, okay? The lower bounds we have here, we have sorting. So if you can say that the problem you're trying to solve can be rephrased as sorting, then it's at an n log n. And then searching in a sorted array is at log n. Element uniqueness is n log n. And then we've got multiplication of n-digit numbers and n by n matrices, okay? So they give an example of what this looks like. And again, this is more math than I'm going to give you, but you can look through that just to have an idea of how we're mapping one problem to the other. Okay. It looks way too much like proofs, which make me happy, but probably do not make you happy. Okay. So then we have this idea of decision trees. Okay. So it's a way we can study the performance of some algorithms that work by comparing items of their input. Okay. So we've got an example here we're going to look at more in detail here in a second, where we're finding the minimum of 3 numbers. So each internal node then represents a key comparison in the node. Okay. And then we've got comparisons that are made based on that. Okay. So we have this decision tree. We start with, you want to see of A, B, and C, which is the smallest. Okay. So is A less than B? If it is, we take this path this way. We say, is A less than C? If it's less than B and less than C, then A is the smallest. Okay. If we say yes, that A is less than B, but no, that A is less than C, then C becomes the smallest. Okay. In the same way, if A is not less than B, okay, and B is less than C, then B is the answer. If not, C is the answer. Okay. So this gives us an idea of how we can find that solution. Okay. So when we look at this here, so as it says here in 11.1, theorem 11.1, the central idea behind this model lies in the observation that a tree with a given number of leaves, okay, that all have, it's a binary tree. Okay. We've talked about that. I assume you talked about it in data structures. Okay. We know that the height of a binary tree with L leaves and height H is the log 2 of L. Okay. So from that, we can figure out that this is going to be a log 2 of N problem. Okay. When we look for the decision trees for sorting, the comparison-based ones, okay, here's an example for sorting. It gets a little more complicated than just finding the minimum. Okay. We still start off with the A less than B. Okay. We then have to ask other questions. So again, following the left, we say, is A less than B? Yes. Is A less than C? Yes. Okay. So we know A is the smallest, but then we have to worry about B and C. So we get their final placement here. Okay. So note that we have B less than A here and also here. Okay. And it's just something that we need to do because we have to get for the outermost, for the A, and then the B and C have to be done separately, no matter what the first thing is. Okay. So that gets us through more math than we care about using Stirling's formula to an n log n, okay, which is what we know for our sorting. Okay. So here's the decision tree for a 3-element insertion sort, one of the sorts that we did. Okay. So we're going to go through with this. Okay. We have A less than B. Yes. B less than C. Get you to this one. Okay. And so forth. Okay. So we have a decision tree also for searching a sorted array. Okay. So on this one, we're going to start at A1. Okay. And see that is it less than, equal to, or greater than A0, A1, oh yeah, of what? That's weird. These always confuse me. Okay. Smallest possible number of comparisons. We're a 3-way comparison here. We're to see whether K is less than AI, K is equal to AI, K is greater than AI, right? Okay, so I'm not sure what that's saying there. You read things and then they confuse you when you see them again. Okay, so we're looking for the ternary decision tree for a binary search in a 4-element array. Okay, so in that case, oh, now it makes sense because it's a binary. The 1 is the middle element. That's what I was missing. The 1 seemed too early to be middle. So this is the middle element. It's either the same or we split it in half again. And from that, we know it's either in the first half or the second half, split that in half again. And because there ends up being 1 on one side and 2 on the other of the middle, we get another layer over here. Okay, that makes more sense. Okay. So that's the idea behind this decision trees. that you're just going to go through and do them bit by bit, okay? And then by looking at all the possibilities you have, you see how many steps that it has to take and what the best case and worst case scenarios are, okay? Of course, for really big problems, that gets to be a difficult task, okay? So 11.3 is more theoretical than the other sections, okay? And when we're looking at these, the computational complexity of the problems, we're always wanting to know if a problem can be solved in polynomial time of some algorithm. A polynomial time just means that most of the problems that are in polynomial time are no more than a factor of 2 or 3, like a cubic at most. So polynomial time is going to be reasonable in ways that a factorial or exponential are not going to be. Okay, so that's kind of the idea here. Okay, so we have some definitions here. If we say that an algorithm solves a problem in polynomial time, and if its worst case efficiency belongs to the big O of P sub n, where n is a polynomial of the problem's input size. Okay, again, could be n or n squared or whatever. Okay, so logarithmic times also solve this because we're using big O and logarithmic is better. Okay, so anything that has that characteristic, we're going to say that they are called tractable. Okay, if they can't be solved in polynomial time, we call them intractable. Okay, so that's the basic definition there. Okay, so again, it goes through how the fact that the polynomials don't tend to be super gigantic. Okay, and that it just turns out to be a convenient way to do things. Okay, so also polynomial functions have many convenient properties. Okay, so the sum, the composition of two polynomials are always polynomials too. Okay, so once this decision was made to make this the cutoff between what we consider relatively efficient tractable problems and intractable problems has led to this whole theory called computational complexity, okay, which seeks to classify these problems according to their difficulty. Okay, so again, that's a whole world of math we're not going to get into, but it does get us into this idea of P and NP. Okay, so we're going to think about these as problems that can be solved in polynomial time are going to be called P. Okay, so the formal definition only involves decision problems, which are yes, no, but we can often rewrite our problems that we may not think of as yes, no problems. Okay, so again, definition 2 then, class P is a class of decision problems that can be solved in polynomial time by deterministic algorithms. Okay, so we're going to call this class of problems polynomial. Okay. Okay, so let's see here. So you can question, as it says here, whether every decision problem can be solved in polynomial time. The answer turns out to be no. Okay, there's some problems we call undecidable. Okay, as opposed to decidable. One of the famous examples was given by Alan Turing in 1936, and this is called the halting problem. Okay, so if you're given a computer program and an input to it, you want to determine whether the program will halt on that input or whether it will continue working indefinitely on it. Okay, the proof of this is surprisingly short. Okay, it's a proof by contradiction. Okay, if we assume that A is an algorithm that solves the halting problem, that is, for any program P and input I, then this A, our algorithm, if it gets the P and the I, will return a 1 if the program P halts on input I. It will return a 0 if it does not halt. Okay. And now we're going to do something that leads to, if you've studied much mathematics, to a very similar thing that Bertrand Russell did in Russell's paradox. Okay. We're going to consider a program P as an input to itself. Okay, and we're going to use the output of the algorithm A for pair P to construct the following program, Q. Okay, so Q we send to P. It will halt if program P does not halt on input P, and it will do not halt does not halt if P equals 1. So if the program P halts on input P, okay? And if this is making your head spin, it's not the end of the world, but it is an interesting little proof here. So then when we substitute the Q for P, we get the following. Q of Q halts if program Q does not halt on input Q. And it does not halt if program Q halts on input Q. Okay, so this is a contradiction because neither of the two outcomes for program Q is possible. So that completes the proof by contradiction. Okay, again, if you don't get it, don't worry about it. But it is an interesting and surprisingly short proof and a good proof technique if you're into those kinds of things. Okay, so here are some of the best known problems that we talk about in these category of intractable problems. Okay, the decidable but intractable problems. So there are a number of these, but not that many, surprisingly. Okay, and these are the most important problems. Okay, that have no polynomial algorithm yet, nor has the impossibility of such an algorithm been proven. So we have the Hamiltonian circuit problem. That's to determine whether a given graph has a Hamiltonian circuit, which is a path that starts and ends the same vertex and passes through all the other vertices exactly once. We have the traffic salesman problem. Find the shortest path through n cities with known positive integer distances between them. So again, this is a Hamiltonian circuit in a complete graph with positive integer weights. So those are connected problems. We have the knapsack problem. Find the most valuable subset of n items of a given positive integer weights and values that fit to a knapsack of a given positive integer capacity. We have the partition problem. Given n positive integers, determine whether it's possible to partition them into two disjoint sets with the same sum. Okay. There's the bin packing problem. Given n items whose sizes are positive rational numbers not larger than 1, put them into the smallest number of bins of size 1. Okay. There's the graph coloring program, a problem for a given graph. Find its chromatic number, which is the smallest number of colors that need to be assigned to the graph's vertices, so that no two adjacent vertices are assigned the same color. Then we have the integer linear programming problem. Find the maximum or conversely minimum value of a linear function of several integer valued variables subject to a finite set of constraints in the form of linear equalities and inequalities. Okay. So these are problems, not all of which are decision problems, but you can turn them all into a decision problem. Okay, if you kind of work them around. Okay. So the definition here, we've talked about deterministic algorithms, okay, where we know what's going to happen. A deterministic algorithm is everything that we've done so far. Okay, you know where to start, where to end. It's all determined. A non-deterministic algorithm then is a two-stage process. Okay, and these are the kind of problems that checking the answer is straightforward enough, but we can't solve the problem directly. Okay, so we do this by going through this non-deterministic guessing stage. So an arbitrary string is generated, okay, that meets what we think are the criteria for being a solution. We then test or verify whether or not that is a reasonable, whether it's a correct solution, okay? So these non-deterministic algorithms then, we say the solves decision problem if and only if for every yes instance of the program, then our algorithm will return the yes on some execution, okay? So it will be able to guess a solution at least once and be able to verify its validity, okay? And we never wanted to answer output a yes for that should be a no, okay? So if we have this non-deterministic algorithm that by guessing in some way, we can come to an answer, okay? Then we say this is a non-deterministic polynomial if the time efficiency of the verification part is polynomial, okay? So then that gets us to this class NP of the class of decision problems that can be solved by non-deterministic polynomial algorithms. We call this non-deterministic polynomial, okay? So most decision problems are in NP, okay? And we say this because P is a subset of NP, okay? And this is true because if the problem's in P, then we can use the deterministic polynomial algorithm that solves it in the verification stage, okay? And we'll just kind of ignore the string generation part, okay? So we know that's to be the case. But this is, as it says here, the most important open question in theoretical computer science. Is P a proper subset of MP, or are they the same? Okay, so does P equals NP? Okay, if P equals MP, it implies that there are many hundreds of difficult combinatorial decision problems that can be solved by polynomial time algorithm. Okay, just because we haven't found them yet doesn't mean that they don't exist. Okay, and most, or at least many, well-known decision problems are known to be NP complete. Okay, which also cast doubt on the possibility that P is equal to MP. So let's look at NP complete, and then we'll be about done because this is a lot. Okay, so an NP complete problem is a problem in NP that is as difficult as any other problem in NP because it can be reduced to any other problem in polynomial time. Okay, so this is a fairly astounding fact if you've been with me this far. Okay, so if we have a decision problem D1 is said to be polynomially reducible to a decision problem D2 if there exists a function T that transforms an instance of D1 to an instance of D2 such that the T will map all the yes instances of D1 to yes instances of D2, and the same for no instances, and that T is computable by a polynomial time algorithm. Okay, so that's what it means to be polynomially reducible. Okay, so then we have a decision problem said to be NP complete if, first off, it belongs to the class NP, okay, and that every problem in NP is polynomially reducible to D that we're trying to say that is NP complete, okay? So they give an example here of how we can map the Hamiltonian circuit problem and reduce it to the traveling salesman problem, okay? I'll leave that for you to read, but if you like, okay? So again, the way this works as NP complete has grown, okay, that once you can reduce, you have a set that we know of that are in NP complete. So to get another element of NP complete, you just have to show that it's NP and then reduce it to just one of the others, because if you can reduce it to one of the others, you can reduce it to all of the others, okay? So yeah, I mean, it's interesting. I don't know that we'll ever know whether P is equal to NP or not, but it's still important to know what that means and what these problems are all about. So hopefully that was clear. If it's not clear, let me know, and we can go through some more detail on that. Again, I'm not going to ask you questions that are going to be anywhere near the proof kinds of things, okay? So I don't think there's much else that I care about at this point in this next chapter, okay? With the numerical analysis. Yeah, I think we've done enough. We're not going to worry about this section, okay? So I'll put some homework out there from the first 3 sections. I'm going to keep them fairly general at this point, okay? And this is our next to last week of regular classes, okay? So we have this week, and then we have next week, and then we have the exam. I'll have to double make sure that I've got my weeks correct, but I think that's the case, okay? So next week, we're going to finish up on chapter 12, which should be right here, on coping with these limitations of algorithm power, okay? So we know now we have some issues in solving all problems in a polynomial fashion. So the question becomes, practically speaking, what are we going to do about it, okay? So chapter 12 will talk about some ways or some techniques we have for trying to figure out what we're going to do about it, okay? So I know this was a lot of theoretical heavy lifting this week, okay? So read through it, ask questions if you need to, and you'll have a better idea what I'm expecting you to get from it as soon as I can post the homework, probably tonight, but it may be tomorrow.